In our last few lectures, we have been studying about the inverter switching characteristics. So आज के लेक्चर में हमने जो NAND गेट है उसको पढ़ना है कि उसकी DC कैरेक्टरिस्टिक्स बेसिकली क्या होती हैं, उसको आप किस तरह से एनालाइज कर सकता हैं. So this is a start towards the complex circuit analysis. Now after this lecture, you will be able to analyze how the complex circuit behave regarding the rise time, fall time, and maximum switching frequency. So the analysis of NAND gate means like we are moving to a complex logic network. Here you can see that we have, like in an inverter circuit, we have only one PMOS and we have only one NMOS. Now we have like multiple gates, like we have two NMOS and we have two NMOS. Like two NMOS are in series, and two PMOS both are in parallel. So we can apply the same basis, like the same basic calculations which were introduced for inverter. So we can use all those calculations which we have done for the inverter, we can apply to this NAND gate analysis. And what we have to do is we have to apply we have to examine the DC and transient characteristics. We have to study both these characteristics of these NAND gates. We have been talking about inverter circuits. Now what we have to understand, what are the complexities in these complex logic circuits. If you see in this diagram, you can see that there are multiple gates that are connected to a node. Like if you're talking about this node, there are like three gates. One is this PMOS, the other one is this PMOS, and then we have one NMOS. So these three gates are connected to this output node. So it means these three gates contribute towards the calculation of rise time and fall times. So the calculations are not as simple as we have been talking about for the inverter circuits. And similarly, MOSFETs are connected in series. We don't have much of the problem when we have our PMOSs are connected in parallel, but we have issues with series connected MOSFETs. Like either they are in PMOS like pull-up network or in our pull-down network. So there are issues which need to be resolved. So let us analyze this NAND gate circuit and how can we calculate the rise time and fall time, and obviously different characteristics which include the power dissipation and maximum switching frequency as well. So how can we calculate those using for this NAND gate?
So हमें एक एग्जांपल देखनी है कि डीसी कैरेक्टरिस्टिक्स जो हैं वो लॉजिक गेट्स के क्या होते हैं, उसका ट्रांजिएंट रिस्पॉन्स जो है बेसिकली कैसे होता है और वो कितना डिफरेंट है फ्रॉम एन इन्वर्टर. तो उसके लिए हम एक एग्जांपल देखते हैं कि फॉर आवर NAND गेट व्हाट वुड बी दी कैरेक्टरिस्टिक्स एंड ऑब्वियसली द ट्रांजिएंट रिस्पॉन्स एज वेल. सो वी हैव टू लुक फॉर डीसी characteristics and obviously the transient response. So we have to solve our different functions for these two, these two parameters. So we know that the circuit of the NAND gate is given as the circuit of NAND gate is like we have been studying many times in our lectures. What would be the circuit of our NAND gate? So it was something like this circuit. Like we have two PMOS on our pull-up network which are connected to VDD. Then we have our pull-down network. We have NMOS here which are connected to ground, and our inputs are labeled as VA and VB. Similarly, we have VA and VB. Sorry, this is VB here, and we collect our output from this port. Like this is our output. So we can say that the FETs which are used in our NAND gate have same aspect ratio. So we are assuming कि जो aspect ratio है of our pull-up network FETs or pull-down network FETs both are equal. That is, like PMOS, like 1 and 2 PMOS, both PMOS have aspect ratio of beta P, and our NMOS has an aspect ratio of beta N. It means our both, like MOSFETs and MOS and PMOS, both are using same aspect ratio, same aspect ratio for our MOSFETs. So like we have here, if you see here in our like circuit, we have these two FETs in parallel and we have these two FETs in series. So we have different type of behavior for series and parallel. So we can say that like this behavior will be different than our inverter circuit. So this behavior cannot be the same which we have been studying for an inverter circuit. So because there are different reasons. One reason is like we have multiple inputs. Like when we have multiple inputs, this means we will have multiple VDC curves. VDC curve means the voltage transfer curves which we have been studying earlier. If we recall our inverter, the parameters of our inverter, the input parameters of our inverter, we said earlier, like for this inverter type, we said earlier, like when Vin changes from 0 to VDD, this implies that our Vout will be equal to, Vout will vary from VDD to 0 volts. Like we have a case, we have one input source, we can assume when our input changes from 0 to VDD, the output falls from VDD to Vout. Like we have this graph earlier, we have this graph here where we have seen that we have Vin and we have Vout, and when our Vin varies, like Vin increases, so our Vout starts decreasing. So we have something like this curve which was known as VTC curve. So but in this case, when we are talking about our NAND gate, the case is much different. Why it is different? Because we have multiple inputs. So what we have to do is we have to consider like different cases. So assume we have consider different cases, like cases where Vout is high and it goes low on some input. So in this case, we're considering we are considering a case where our output was Vout was high and it decreases, which we have been seeing in our VTC curve, like our output decreases, something like this. So we are considering this case here. If we make a table of our inputs and corresponding outputs, the table would be something like VA, VB and Vout. When our VA is 0, when our VB is 0, this is a NAND gate, our Vout will be VDD. When our VA is equal to 0 and VB is equal to VDD, and our Vout will be VDD again. Same will happen for this VDD and 0 inputs. The output will be VDD. But for the last case, when our input is VDD and VDD, both inputs are high, our output is 0. So we have here 3 different cases where our initial output is high and then it goes to low. Like we have one case here where our output was high. The second case is here when our output was high at initial value, and then we have this third case here when our output was again high. So we have these 3 different transitions where output goes from high to low state. It means our output was initially VDD, and when the value changes, like for example this was VDD and this was 0, and when VB changes to VDD, this goes to 0 volts. So there will be a curve that represents an output, a VTC curve. Similarly, this is our second case where our output goes low, and this is our third case where our output goes low again. So we have 3 different cases. The first case happens when both inputs goes to VDD simultaneously. Like we have initial values here, like VA is equal to 0 and VB is equal to 0, and both values VA and VB like changes to VDD, these 2 values here. So we can say that in case 1, our both inputs goes to VDD simultaneously. So what that means is we will have a curve that will be a different curve than these two conditions here, like condition 2 and 3, because the switching will be different. So this case is known as a simultaneous input switching. Simultaneous input switching. So this is our case 1, and we can take case 2 and 3 as a common case. Like we have case 2 and 3 as a common case, because like in both cases only one input goes from 0 to VDD volts. So like only one input goes to VDD. So like depending on these 3 different inputs, like switching, we have 3 different curves, 3 different VDC curves. So we can plot it like here. We have our V out here, we have V in here, and we have 3 different curves. The first curve is like we will plot a first curve that was for simultaneous switching. This was here, and then the second curve can be plotted as it starts from the same value, it goes low earlier, and then we have like higher voltage. Then we have another curve, like let me draw it with different color. So we have a different curve, it goes low earlier, and it achieves a maximum of VDD value. That this one is our VDD value. So this curve, like this represents our curve 1, this represents our curve 2, and this represents our curve 3. So we have here 3 different curves. Like obviously they are not at the same level. If they are not at the same level, which means the VM is different for all these curves. Like this curve has different VM value, and these both curves have different VM value. And we also have learned earlier, like the shifting of these curves, is because of beta n or beta p, like this ratio here. This ratio defines where the curve will lie. Like either it will have a delayed version, or it will have a smaller version, it will drop down earlier. So this curves basically depends on this Vm. So we will see a bit later why we have this curve, the one curve here, the first curve here, that is shifted on the right side, and what will be the benefit of this curve. So what we have to do is we have to calculate the Vm value. Like we have to calculate the switching value of this curve here. This first case here. The first case was of our simultaneous switching case. So let me draw first here the diagram of our NAND gate. That will be helpful for us to calculate the Vm values. The diagram of our NAND gate is like we have our PMOS here, and we also know that we have a NVL here, and we have two inputs, so we can draw two gates, and we have our PMOS here. So let me draw it with different color. Like we have our PMOS here. The width of PMOS is different, and we have the connections, the input and output connections. So for our PMOS here, this is connected to this port here. So we have the connectors here at this point, and these points also have connectors, the contacts. And we have this point connected to ground, like this one is our ground, and this one is connected to output. So we can draw it like this one is connected to our output. So we have contacts here at this point, we have contacts at this point. So this represents our out. These are our inputs VA and VB, and this one is connected to VDD, and this one is connected to ground terminal. So this was our overall circuit for our NAND gate. We can see that here the width of our PMOS is represented by WP, and width of our NMOS is represented by WN, and obviously the channel length is represented by L. This one is channel length, and obviously this one is also our channel length. So the channel length is basically same for our both PMOS and NMOS. So we assume a case where we have VA is equal to VB, and both are equal to VM, like both are equal to at midpoint voltage. So what would happen, like both gates are at same potential. So now we have to consider one by one. Like first we will consider the NMOS, and then we will consider the PMOS. Like how can we model these two different pull-up and pull-down networks. So if we first consider the NMOS. For the NMOS case, like let me draw it again, only the NMOS circuit. The NMOS circuit was like this. We had two gates here, and we had like a metal connected to this terminal, and we have another metal that is connected to this terminal. So it means these two gates are parallel. If these two gates are parallel, we have to simplify them. Wn, this is length L, and like we have input voltage Vm and also Vm. So the equivalent circuit could be equal to, we can merge like this area here, the NMOS area and plus area. The equivalent circuit would be having same width like Wn, and we have one common gate, like both gates are common here. So we can say that we have here two common gates, like we merge these two gates here. So we have this point here, like this point here, that is connected to ground, and this one was connected to our output. So we are merging two different gates, and if we merge these gates, we see that we have applied same voltage on these two terminals. So that's why we are combining these two gates. And we also can observe that this length is now 2L. This length is not the same like which we have been mentioning it here and here. Like now we have double the length of our channel, and also the width remains the same. Like width is same for both, and for both our NMOS. So we are combining or merging these two gates, like one gate here and one gate here. We are merging these two gates because NMOS N plus regions are common. So we are ignoring that like N plus regions because they are at the same potential. So we approximate it by NMOS which has double the channel length, and we can say that the aspect ratio is now Wn by 2L. So the updated aspect ratio is W by 2L, and the equivalent transconductance is given by, that will be equal to beta n by 2. So it was earlier, it was assumed to be beta n. Now this is estimated by beta n by 2. So this is the case when we consider our series connected NMOS, like series connected NFETs. So now what we consider is, we have our PMOS case where we have both PMOS connected in parallel. So for our PFET, let me write it as PMOS. So now we will consider a PMOS case. In our PMOS, we have drawn it like we have two parallel connected MOSFETs. We have same value, like same diagram where we had two gates. Then we had like these terminals connected together. So we had like here connected, and then we had our output connected here. So these two gates are parallel connected. The length of our both gates is L and L. The width is WP, and obviously the voltage at both the gates is Vm. And the equivalent circuit for our this condition is given by, like we have same width, that is WP. We have two gates here, these are connected in parallel. Then what we can do is we stack them on top of each other. So we will have another PMOS that is on top of like the first one. We will have here one gate, and we then have another gate here. So the total width of this equivalent circuit would be 2WP, and the length is same, that doesn't change, and the voltage applied is Vm. So we can say that the equivalent circuit for a parallel connected MOSFET is given as this, because we are stacking the two gates on top of each other. So the parallel MOSFETs are joined together to give the aspect ratio, which is equal to will be equal to 2WP by N, and beta P will be equal to 2 beta P. Now we are talking about the double transconductance. So the rule to remember for the parallel and series connected MOSFETs is, like, we have to remember this rule where we say when we have a series connected MOSFET, or like obviously it can be NMOS and it can be PMOS. Like for NOR gate, we will have parallel combinations in NMOS case and series combination in PMOS case. So that can be changed. So for a series combination, like a series means, then we have to join our MOSFETs side by side. And for a parallel combination, like stack the MOSFETs on top of each other. So then we will get different aspect ratios that will be helpful to calculate our Vm values. So if we have two different circuits, now we have combined different circuits to get a thicker MOSFET, or we can say that to a MOSFET with different transconductance or different width. So the equivalent circuit can be replaced by the equivalent circuit of NAND gate can be replaced by a circuit which is shown here. So equivalent circuit will be equal to, like, it can be represented by a inverter circuit that has different aspect ratios. So we have our input, we have this gate, this PMOS gate here. It has a transconductance of 2 beta P, and this NMOS has transconductance of beta N by 2. So we have these two different gates which have different aspect ratios. So this input is Vin, and we are considering a case when Vin is applied as Vm, and obviously we know that at Vin is equal to at Vin, which is equal to Vm, the output will be equal to Vout as well. Vm as well. So we can write it in form of Vm. So this circuit can be treated as a NOT gate. Like, treat this circuit and when we solve this circuit for our NOT gate, we assume that at input Vm both our currents are equal. Like the current that flows from PMOS IDP and the current that flows from NMOS IDN both are equal. So the equation for the both currents was equal to, for an inverter, that was equal to So this was our equation for both the currents, which we equated in for the case of our inverter. Now we have some update here. like beta n, we have to replace this beta n by 2, and we have to replace this beta p by 2 beta p. So we can say that if we solve these expressions, then we may there would be some cancellation in our equations. So if we solve this expression for Vm, the midpoint voltage, that midpoint voltage will be equal to like VDD minus VTP plus 1 over 2 rho of beta n over beta p. Then we have Vtn, that is divided by 1 plus 1 by 2 root of beta n by beta p. So this is a new expression for our midpoint voltage. So what difference we have from the previous equation? So we have this different term here, like 1 by 2 here and 1 by 2 here. And from this equation we can also conclude that like beta n by beta p is multiplied by a factor like 1 by 2. This implies that VTC will shift towards to right. Like this is the reason, like this factor is the reason why our VTC curve was shifted towards the right. And what other thing can we conclude from this expression? We assume, or we observe here, like this term 2 here, that comes from our beta n by 2 or 2 beta p. So we have to observe here like this 2 is equivalent to this 2 here. Or we can also write, if we have n number of transistors, we can write it as beta n or n beta p. So this term will be equal to 1 over n here. Like we can replace this term here, 1 over n. So if we increase number of transistors, then our beta p, the beta p will shift towards more, like the beta p will shift to the right as well. So we can say that if we increase beta, this means that we are shifting to left, and if we decrease this value, this implies that shifting to right. So if we have n NAND gate and input NAND gate, this factor will be 1 over n. That means the VTC curve will shift more towards right. So this was a basic understanding how can we calculate our midpoint voltage. Now we have to observe that how different inputs, multiple inputs, affect our rise time or fall times, how they are affected, and how can we calculate rise time and fall time for multiple input circuit. Or we can say that the input which has multiple MOSFETs. So we have to consider different circuits. For example, to solve the circuits for our transient response, so we have to solve the calculations for transient response. Let us consider a circuit that is something like this circuit here. We have our two MOSFETs, then we have our NMOS, like this NMOS is connected here. This NMOS, sorry, this is our NMOS, this is not a bubble here. So we have our NMOS here. We have one output capacitance that is connected at our output, like at this node here. This is our capacitance C out, and we know that this may be a value of V out. And we have VB input here, we have VA input here, these are like tied to ground. We have VA here, we have VB at this terminal. These are connected to VDD. So this is our circuit for our for our NAND gate. One thing we have to mention is like this is our RP, this is also RP, this represents RN, this represents RN. What we have an extra here, like one extra node here, like this node here. At this node we have a capacitance that appears between two NMOS, two like our NFETs. So this capacitance is represented by Cx. Now when we have to solve the transient response of our NAND gate, we have to consider this Cx here. So we can say that here in this circuit the output capacitance C out is given by CFET plus C load. So we have these two values here, like one is our load capacitance, this is our load capacitance, and this is our FET capacitance, like FET capacitance that appears at our output, like that appears at this node here. So we can say that at this node we have three different gates connected to this node. Like we have two NMOS, sorry, no, we don't have two NMOS, but we have only one NMOS here that is connected to this node. We have two PMOSs which are connected to this node. So we have the total CFET will be equal to, this will be equal to like CDN plus 2 CDP, because we have two PMOS that are connected to at this node. So like this means like this one is because of our NMOS and this one is because of our PMOS, like because we have two PMOS connected to an output. And this RP and the resistance of our PMOS and NMOS can be represented by, like RP will be equal to 1 over beta P, and this is VDD minus VTP, and also Rn is represented by beta N VDD minus VDN. So these are the values for our resistances of our like PMOS and NMOS. The Rn and Rp represents the channel resistance of our MOSFETs. So for transient calculations we have to find RC time constant for TR and TF. So now we have to solve RC time constant for obviously rise time and for time. We have to solve both for for both cases. So what we need to do is we have to look for worst case values. Like obviously we are not here to design best case values, we have to check for the worst case switching values, like what will be the worst case switching time. So first we will consider the rise time, that is represented by TR, and we will solve for worst case, and we will discuss a bit later why we are not talking about the best case values. So for the rise time we know that we have to consider the pull-up network. So we will consider the PMOS, like PMOS of our circuits. We have observed that for our NAND gate circuit we have two different PMOS that are connected parallel. So the V out is 0, like we consider that our V out was equal to 0, and it goes to VDD in our like rise time case.
So if we consider one PFET, because both are connected in series, so we are assuming like in case 1 we are considering only one PMOS that is connected to that is connected to VDD, that is conducting. So for our case 1, which is our worst case, we consider like only one PFET is conducting. If our one PMOS is conducting, then Cout can be like the Cout circuit will be charged through the RP capacitance. So for this case, when our one PFET is conducting, the equivalent circuit is given by like this resistance here. Then we have this node, the output node here. Then we have output capacitance like this Cout here. This is our cutoff, like our NMOS is cut off, like this is not conducting. So we can say that the current flows to this capacitor, that is Cout, and we can represent it as I charging current that flows from RP from VDD through RP towards the Cout, and also this has output voltage of Vout. So the Cout capacitor charges, like this capacitor charges through RP resistor, and this implies that an inverter circuit equivalent, like this is an equivalent circuit of our inverter. So we have seen this solution earlier, so we can write it directly like Vout of T will be equal to VDD 1 minus epsilon minus tau divided by tau P. So we have seen this solution earlier where the output voltage that is dependent on time can be written as this expression. Here the tau P will be equal to RP Cout, and the rise time will be given by the R is equal to 2.2 tau P. And we can also observe that we can also write this expression in another form, which was equal to TR was equal to like T naught plus alpha naught CL, and we had said it earlier, the T naught is equal to 2.2 RP CFET, and this phi naught was equal to 2.2 RP. So this was equal to RP, and obviously this is CL is different, and this represents this term represents slope of our rise time here, because we said that the rise time depends on our load capacitance. If the load capacitance increases, the rise time also increases linearly with increase in the capacitance. So this was our case 1 when we considered like one FET, like here we considered one FET that is conducting. But in case 2, if we consider both FETs, like both PFETs, if we consider both PFETs are conducting, what would happen then? If our both MOSFETs are conducting, the equivalent circuit would be like this. We had like this output capacitance here, and this is cut off, like the NMOS is cut off. This is our Cout, we have RP, and we have another RP here. This is connected to VDD node. So if we have parallel transistors, like parallel transistor means total RP will be, the effective RP will be RP by 2, like it will be divided in half. This implies that this is our
like best case value. Why it is best case? Because if we solve this expression, we will get the expression to be the tau p will be equal to, like this will be equal to, Rp by 2 C out. So it means that this tau p is reduced. If this tau p is reduced, we can also say that this expression, that is 2.2 tau p, this is also reduced. This means that if we have two MOSFETs that are connected in parallel, we will get a faster rise time. A reduced rise time means our signal will rise earlier. So that is the best case value. So in our circuits, we don't consider the best case solutions, because we have to design a circuit that can tackle worst case conditions. So we have to design, whenever we design our circuit, we will consider the worst case values. So to calculate the fall time here, the fall time calculations are a bit like complex. They are not simple as we consider for the rise time in our NAND gate circuit, because these in our fall time calculations, we have two MOSFETs that are connected in series. So whenever we have the MOSFETs which are connected in series, the calculations will be tougher as compared to the MOSFETs which are connected in parallel. So in this case, the equivalent network could be equal to, like we have one NMOS here, the other NMOS is connected in series here, and they both are connected to ground. This output node is connected to C out node here, that is connected to ground. We have C out here, the plus and minus values represents our V out, and also the current, like the circuit will discharge from this path. This current is known as I discharge, IDS. I represent it as 1. Why obviously I represented this case as 1? Because there is another capacitance that basically appear between two NFETs that we had seen earlier in this lecture. So we have this capacitance here, the another capacitance that appear in between these two like MOSFETs. Like one MOSFET is here, the other MOSFET is here, like these two MOSFETs, and we have different capacitance, and this capacitance is known as Cx. And this capacitor just discharges through this path, like this from this node here, the capacitor that charges through this Rn value, like from this Rn. So we have two different currents. One is known as ID discharge 1 and one is known as I discharge 2. So what would be the worst case here? The worst case would be the Cx is charged at its full. So when our Cx is charged, and that obviously would be a worst case, because it will discharge through one FET to ground. So because it is fully charged, so it will discharge through or one FET to ground. Like this capacitor, Cx capacitor, will discharge from this this Rn node here. So we can also say that the current through NFET is limited by WL ratio. Like we have seen it earlier, the current is limited by the aspect ratio that is given by W by L. And if we model this discharging behavior, this discharge modeling would be the discharge modeling can be represented by, like, V out of T will be equal to VDD epsilon of minus T divided by tau of N. And if we use the Uyemura formula, we can write it as tau N is equal to C out Rn plus Rn, because we have two resistors in series, plus a capacitor Cx, and then that discharges through Rn. So this is our the tau N. And why we write it like this? Because we are using a superposition of time constants. So we are using superposition of time constants. And we can also write it in a different way, like we can say that tau N is equal to tau of N1 plus tau of N2. Like this is because of 2C out Rn, and this represents Cx Rn. And fall time, like Tf, is given by 2.2 tau of N. And if we replace the values in place of this tau N, we will get Tf is equal to 2.2, like this is Cfet plus Cl 2 Rn plus Cx Rn, and like this represents C out here. So if we rearrange the expression, we will get Tf is equal to 2.2 Rn 2Cfet plus Cl. Sorry, this is not Cl, this is Cx, and plus 4.4 Rn. Sorry, this I have tried it as 4.4 Rn and Cl. So this is like, this represents, the first term represents zero load, and the second term represents, like, not the second term but the constant here, the 4.4 Rn represents slope of Tf. So the slope of Tf can be represented by this expression. So what we conclude from this derivation here, from the derivation of our fall time, what we conclude from this, this derivation of fall time, is that this zero load and the slope, they both are affected from series connected FETs. So we can write it as both are affected from series connected FETs. So this implies that series connected FETs, they results in longer delays. So how can we represent this claim here in mathematical form? If we rewrite the expression for tau of n, that is equal to this tau of n was equal to C out Rn plus Rn plus Cx Rn, or if we rewrite this expression as Rn 2C out plus Cx, here we can say that C effective value, the effective value of our capacitance is 2C out instead of C out. It means that our capacitance is increased, that basically represents in a more time to basically discharge this discharge capacitor. So we can say that the series connected MOSFETs have higher capacitance as compared to the parallel connected MOSFETs. So we will have longer discharging time. So we will have a longer fall time here. So this ends our discussion about the DC characteristics of MOSFETs, and obviously we have gone through different stages where we studied, initially we studied about an inverter. We calculated the capacitance which is involved with the inverter. We have seen the input capacitance, we have seen the output capacitance, we have also seen the load capacitance. And then the second lecture, the second video of this series, we have calculated the rise time and fall times, and also we have seen the power dissipation, the maximum frequency limitations, and we have obviously seen the different features for the inverter. And in this session we have explored that how can we apply the same calculations or the same phenomena of an inverter circuit to our different MOSFETs. So using this same approach, you can also solve the rise time and fall time calculations for different complex equations. If you are given with the complex equation, now you will be able to solve that expression, and also you will be able to define what will be the rise time and fall time for the reverse case of that circuit. So this was our last session for the DC analysis, and from next sessions we will be studying about the advanced techniques where we can use different techniques to design our circuits. So this is it for this session. I hope to see you in next video, inshallah.